Okay, I am back, and now we are going to be talking about integrals. So we talked about derivatives. We proved what the derivative of a polynomial is, and now we're going to talk about another concept in calculus, which are integrals, which maybe a lot of you are familiar with, but we will be using them later on in some of our calculations. So I'm just going to start from the beginning, and this will be good review too for those who have been using integrals for a long time to kind of remember the original kind of idea of where an integral comes from. So if we had a function, and let's say it looks something like this, and we wanted to find the area under this curve from, let's say, point A to point B. And we wanted to find this area. Question is, how would we go about that? Well, one way to go about that would be we could estimate it, right? So what I could do is I could say, okay, I'm going to take some rectangles because I know how to take the area of a rectangle. Let's say I take two of them. And let's draw a rectangle right there. And in this case, I would find the area under this rectangle and under this rectangle. And I'd be really close, but I'd be a little bit short because I'm missing that and I'm missing that. Well, I could actually get closer than that if I delete these. Let's go back. And let's say that I decided, okay, I'm actually going to do, I don't know. Let's do, that was a bad one. Let's do like 4 rectangles. Wow, that was actually, those were of different, they should all be of the same size. But you can imagine 4 rectangles of the same size, and I'm missing a little bit of space in each of these sections, but not quite as much as before. And I could take the area of those. Well, the idea of an integral is we're going to make the rectangles smaller and smaller and smaller until we have an infinite number of rectangles in this space, and we're going to take a limit and calculate the exact area. So similar to what we did with the derivative where we took a limit, we're going to apply the same sort of concept here. We're going to take a limit and we're going to calculate an area. So let's kind of formalize this. And first of all, let's also think about what kind of cases where we would maybe want to use an integral. One is, like I said, finding areas under curves. But a more practical application might be in physics when you're calculating work. Work is force times distance, and many times force will depend on distance. And in that case, you can create a function where, let's say this was force, and let's say this was distance. Then we could find the area under the curve, multiply. So when you're doing an area of one of these rectangles, you're looking at distance times force, right? And you're adding those all up to get that area, which would be work over time. So that's just an example of where you might want to use something like this, and there's a ton of examples of where you could use integrals. So anyway, let's kind of formalize this and think about how we want to write this. So let's say, first of all, we want to know that our function is continuous. And what do we mean by let's back up and let's talk about what a continuous function is. So a function f of x is continuous at point C if, and point C is on the real line, if the limit as x approaches c of f of x equals f of c. And then we can further say that the function is continuous if it is continuous at every point c. So that would mean we would have a continuous function on that range. Now, this is essentially just saying as we're approaching this number c, we're actually approaching f of c. So what I mean by that is if I draw a line like this, something that look like that would be a continuous function. You know, let's say that's c. As I get closer and closer and closer and closer to c, I approach f of c. So what would actually really help is to show you what a non-continuous function might look like. And that would be something like this, where you might have a function that goes like this, and then maybe like this. So you just have this gap here, and let's say that's point C. So there you're actually approaching infinity as you approach C, and same with going from this side. You're also approaching infinity as well, and you're never hitting a point there. You kind of have this break, and so that would be a non-continuous function. There's a lot of examples of non-continuous functions, but for our strict definition of an integral, we need to have a continuous function for what we're going to be looking at right now. So let's say that we are given f of x. This is our function. We're given that f of x is continuous on the range a to b. Many times we'll denote ranges with the brackets. A closed bracket like that means that it includes the point. An open bracket would mean that it does not include the point. So let's say we have a continuous function on that range, and we're going to divide. So, and we divide, I'll write that out, this into in subintervals. And this is getting to the idea of the rectangles that I was telling you about at the beginning, of length b minus a divided by n. So what I mean by that is, if we, let's say we had, let's say we were going from 1 to 4, the length of that range is 3, right? And let's say we wanted to divide that into 10 rectangles. 3 divided by 10, we would do, each would have a width of 3/10, and then you add 10 of those together, and you're going to get a length of 3 within that range. Yet we're going to actually have this number go to infinity, which I'll tell you about in a minute, but that's kind of the idea of dividing that section up, or that range up. So let's kind of go back to where I was. So here I was saying a and b, so b minus a divided by n. And what we're going to do is we're going to choose point xi star. I'll tell you what that means in a second, in each interval. Each interval. So what xi star is we're saying within the ith interval, we're going to choose some point. So let's say our function looked something like this, and we had a couple of rectangles in here, something that looked like that. And let's say we're looking at the second interval, so that would be I equals 2. Xi star means we're choosing any x on this line. We can choose any one we want. And then what we're going to actually end up doing is making our rectangle the height of f of xi star. So in this case, I actually chose my point to be the very end, the very left end, because that is the point I'm choosing to go for my height. But I could have actually picked my height to be this one if I wanted. So I could have had the whole rectangle look something like that, you know, or I could have picked one of these other ones. because we're just choosing any x within that range to pick our height. It's not going to matter. The rectangle will vary just a little bit, but ultimately when we go to infinity, any of those points are actually going to give us the exact same value, so it's not going to matter. So again, the I denotes the interval that we're in, and then the star is what denotes any random point you choose within that range. That's what the star means. Okay, so we've gotten some language out of the way. Then we are going to define what's called a definite integral. The difference between a definite and an indefinite integral is choosing a range. So we're doing a definite integral because we're going from a to b. So the integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of xi star change in x. This is the definition of a definite integral. So what we're saying is for I is equal to 1 to n, so that's choosing each of our subintervals, so that's looking at each of our rectangles. Let's say rectangle 1, rectangle 2, rectangle 3, rectangle 4. We're looping through and we're saying, okay, first pick our point in that range and then take the y value. So that's the height. And so what's an area? Area is a height times a width. So there's our height. Change in x is just the width of the rectangle because we said that change in x was equal to, let me put that in parentheses down here, change in x equals b minus a divided by n. That's what we picked right up here. So that's just the width of the rectangle, and we're multiplying the height times the width. We're summing all those up to get the total area, and then we're taking the limit as n goes to infinity. So we're saying divide those rectangles up into, or create an infinite number of very small width rectangles, essentially, is what we're doing. We're adding those up, we're getting the area in between, and that is the definition of a definite integral. So if you were to kind of think about this, let's actually, what we should do is we should think about an example. So that is the formal definition of an integral. Let's go to the next screen here and let's think through an example. So let's say, for example, I was trying to take the integral from 0 to 2 of x squared dx. So that's my function. And what does x squared dx, or what does x squared look like? Let's kind of draw a picture. 1, 2, 3, 4. 2, 3, 4. So let's say that's x. And we'll say this is f of x. Let's go 1, 2, 3, 4, 5. 1 squared is 1, so we're going to go there. 2 squared is 4, so that's going to be right there. 3 squared is 9, which is going to be way up, so it's going to look something like that. It's going to be a curve like that, and we're going from 0 up to 2, and we're looking at this area is what we're trying to calculate. Okay, so we're going to calculate this the long way using that definition. What I'm going to later show you in another lesson is a shortcut which many of you are used to. Some of you may not have not seen, and it'll be a good reminder. This will be a good reminder of the tedious way of doing this. So let's clear the screen here. We kind of know what our goal is now. So f of x equals x squared, and we're taking the integral of x squared dx from 0 to 2. First, let's calculate the width of our rectangles. So that's going to be our change in x, right? From the last screen, we knew that was b minus a divided by n. So here, b is 2, a is 0, so we're going to do 2 minus 0 divided by n. N is what we're taking the limit on. So 2 minus 0 is 2. We're left with 2 divided by n. That's the width of each rectangle. So if you kind of think about it, each of our intervals that we're dividing this up into is going to be 0 to 2 over n would be our first one. The next one would start at 2 over n, and it would go a width of 2 over n. So 2 over n plus 2 over n is 4 over n is what it would end at. You can kind of see where this is going. The next one would be 4 over n up to 6 over n, dot, 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 dot. It would keep going. So our ith interval would look like, let's do some dots there. Our ith interval would look like this. It would be 2 times I minus 1. Because like this one here is our second interval, right? So if I were 2, I minus 1, 2 minus 1 is 1, 1 times 2 is 2, so that's our 2 over n. So 2 times I minus 1 over n up to 2 times I over n. Because like this one over here, for example, if we're in the second interval, 2 times 2 is 4, and that's how we get the 4 over n. So that's just a general way of writing the ith interval. Dot, 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 all the way up to the n. We're going to be at 2 times n minus 1 over n 2. Because we're ending at 2, right? That's our b up here in the integral. That's the 2. So that's what we're dividing our 0 to 2 up into all those intervals, each of length 2 over n. So let's next choose our xi star in each of these. Like I said, you can choose any point within the interval. And actually, we're looking at the ith interval. We should look at the general form there. So what we're going to pick is we're going to pick the right endpoint, just to pick a point in there. So I'm going to pick this to be my general form of the point that I'm going to pick. So xi star is equal to 2i over n. Okay, so now we've kind of picked what our point is going to be in each of these intervals. We've kind of defined our interval, and now we can kind of formally write out a few things. Okay, so let's look at the summation from I equals 1 to n of f of xi star times the change in x. Because that's what we're going to be taking the limit of. That's, the definition of the integral took the limit as n goes to infinity of that. But first, let's actually simplify this expression, and then we'll take the limit after that. So this is equal to the sum from I equals 1 to n. F of xi star we chose to be our right endpoint, which is 2i over n, times change in x, which we calculated to be 2 over n on the previous screen. Okay, so let's simplify this a bit. So this is our function, right? Our function is x squared. When we plug 2i over n into x squared, we're going to get sum from I equals 1 to n of 2i over n squared times 2 over n. Now we can simplify that even further. The sum from I equals 1 to n of, 2 squared is 4 times 2 is 8, so we're going to be left with 8 times I squared over n squared times n is n cubed. All right, you'll notice that we are summing on I, right? You can see the summation starts from I equals 1 and goes up to n. So really the summation is only depending on the I, which means we can pull out anything other than an I. So you can notice that I can pull out 8 over n cubed. And then we're left with the sum from I equals 1 to n of I squared. So this is starting to look a little bit nicer. All right. If you recall, I'm not going to prove it at the moment, but there is a proof for the sum of I squared, what that is equal to, or when I equals 1 to n of I squared. So let's first of all write our outside term, which is 8 over n cubed. And this is a special expression here, and you can find it in many textbooks, and the proof is online as well. I may have a video where I end up proving this, but I'm not going to prove it in this video. It's using something called telescoping to prove that. But that is equal to n times n plus 1 times 2n plus 1 divided by 6. There's a few summations out there that are fairly easy to prove, like I squared, I cubed. There's a few out there that it's handy to have that formula, because then you can easily simplify things. So this is a bit nicer. Now we can kind of multiply things out a little bit here, and I'm gonna pull my 8n with my 8n, and then I'm gonna multiply this and this. So I'm going to get 2n squared plus n plus 2n, which would be plus 3n plus 1 divided by 6n cubed. Okay, so let's simplify this even further. I'm going to go to the next screen. So let's rewrite that at the top just to have it handy. We had 8n times 2n squared. What did we have? Plus 3n plus 1 divided by 6n cubed. So that's what we've solved for so far. Now let's just kind of multiply our 8n with everything. So we're going to get 16n cubed plus 24n squared plus 8n divided by 6n cubed. All right, so we're taking a definite integral from 0 to 2 of x squared dx. That was our original goal. What did I tell you the definition of that is? Well, it was the limit as n goes to infinity of the summation from I equals 1 to n of f of xi star times change in x. This is the piece that we just solved for x squared and the 0 to 2 interval above. So now what we've simplified to is the limit as n goes to infinity of 16n cubed plus 24n squared plus 8n divided by 6n cubed. Okay, so there's a couple ways you can think about this. When you're going to infinity with n, the higher power terms are what's going to matter, right? So your 24n squared and your 8n are essentially going to be 0 in comparison to your 16n cubed, because the higher the power, the more it's going to matter in the long term. So essentially in your limit, those terms are going to drop out. And we can also use something called L'Hopital's rule, which I'm not going to prove right here. That would take too long to prove right here. I may prove that at some point, which is another way of looking at this limit, and it essentially tells you kind of the same thing, where those terms are going to drop out, but it's telling you that the limit of a function over another function is equal to the limit of their derivatives of the one function over the other function. And there's some special conditions with continuity and things like that, but essentially it's going to do the same thing, where you take the derivative of that, it's going to drop to 8, which will then drop to 0. If you take the derivative again, you can take a couple derivatives of this and drop it to 0, and you're going to eventually be left with your 16 over 6. So there's two ways to think about that. Again, I'm not going to prove the L'Hopital's rule, but what I'm going to tell you is these terms go away, because those are nothing in comparison to a cubic term. So we're essentially left with the limit as n goes to infinity of 16n cubed over 6n cubed, Well, if that's the case, the n cubes are going to cancel and we're left with 16 over 6 is our limit, which is equal to 8 over 3. So our final answer of the area under that curve from 0 to 2 is 8 divided by 3, or another way to say that would be 2 2/3 would be the area under that section. So again, that was the long way of calculating that integral, and I'll be teaching you a shorter way to do so, but it's good to know how these things work and why it works before we end up, using all these shortcuts. So that is the video on integrals, and I hope you enjoyed.